Celestial objects, lunar phases, eclipses, and the seasons. So this is what we're going to look at in this lesson. So the learning outcome, students should be able to develop and use a model of the Earth, Sun, Moon system to describe predictable phenomena observable on Earth, including the seasons, lunar phases, and eclipses of the Sun and the Moon. So what will we look at in this lesson? So the learning intentions. So we look at the Earth and its rotation and its revolution. So how the Earth rotates on its own axis, and then how the Earth also revolves around the Sun. The day and night cycle. So what causes day and what causes night? Earth's axis tilt. So the Earth is actually on an axis, but it's slightly tilted. We look at what effect that has. Day length. So for example, how long a day is. So we know as we go through the seasons, the day length changes. Direct sunlight energy. So we look at how the difference kind of between direct sunlight and then sun that's hitting a surface at an angle. We look at the seasons, the solstice and the equinox, moon's orbit and rotation. So how that impacts then on the tides, lunar phases, solar eclipse and lunar eclipses. So Earth's rotation and revolution. So the rotation of the Earth is it's turning on its own axis. So if we take, for example, we can see here, this is a model of the Earth, we can see that it's actually rotating on its own axis. So there's an axis that goes down through the Earth, essentially kind of splits the Earth in half. And the Earth revolves around that, rotates around that. So the rotation of the Earth is the turning on its own axis. So it takes 24 hours for the Earth to make one complete rotation on its axis. So for it to rotate once on its axis, it takes 24 hours. And that's where we get the standard day. That's why a day is 24 hours. It's in the length of 24 hours, or in the length of a day, the Earth has done one full rotation on its own axis. Now, if we relate so the Earth rotates 24 hours on its own axis, with reference to the Sun, the Earth's axis of rotation is actually tilted at 23.5 degrees. So if we take, so this is the Earth, and then this is the axis here. And you can see that there's a slight tilt on the Earth. So imagine this red dot here is the Sun. With reference to the Sun, the Earth's axis of rotation is actually tilted at 23.5 degrees. So it's slightly tilted in relation to it facing the Sun. So at certain points in the year, this half or this hemisphere of the Earth will be tilted towards the Sun, whereas this hemisphere down here will be tilted away from the Sun. So there's that slight tilt on the Earth's axis. So Earth's rotation and revolution. So if we have a look at this diagram here, we can see that the Sun is in the center of our solar system, and the Earth revolves around the Sun. So it has an orbit that it revolves around. So that's this kind of dotted line here. And the time it takes for the Earth to do one full revolution around the Sun is 365.25 days. So that's what's known as a calendar year. So this movement of the Earth around the Sun. And the orbit, so this orbit here, the path that the Earth takes around the Sun, it's not a perfect circle. It's an ellipse, so it's not completely. It's not a perfect circle. So at some points, on its journey around the Sun, the Earth is closer to the sun, and then another point it's further away from the sun. So revolution is the movement of the Earth around an external object, which is known as the sun. The Earth's revolution around the sun takes 365.25 days, or 1 year, so that's where we get our 1 year from. The force of gravity between the sun and the Earth keeps the Earth in a fixed orbit. So there's this force, it's called gravity, and this force is acting, so the sun has a force of gravity in relation to the Earth, and what it's doing is it's essentially moving, it's this force of gravity that causes the Earth to move or orbit around the sun. And it keeps the Earth in this fixed orbit. And it basically stops, if the sun wasn't there, basically the Earth would move off its orbit and move off into space. So the orbit is not a perfect circle. The moon orbits or revolves around the Earth. So then you have the Earth itself, and then around the Earth you have the moon. So the moon is in orbit around the Earth, and the moon also rotates on its own axis as well. Okay, so you can imagine the same way the Earth revolves around the sun, and then the Earth rotates on its own axis. Well, the same thing in relation to the Earth. The moon revolves around the Earth, and the moon also rotates on its own axis. So we can see, so the Earth has an axis that moves through it, and then you have the Earth rotates around its own axis. So Earth spins on its axis, and one complete rotation equals a day and night, which is 24 hours. Okay, so that's the rotation of the Earth around its own axis. Then you have the Earth revolves around the sun, like so. So the sun's in the middle and the Earth revolves around it. So revolution, Earth revolves around the sun and completes one revolution in 365 days. 1 quarter day, leap year, adds a day to the calendar every 4 years. So this rotation of the Earth around the sun is what we call a year. So it's 365 days. And then what happens is, because of the tilt of the Earth, portions of the Earth are on its journey around the sun. Certain portions of the Earth are tilted towards the sun, and certain portions of the Earth are tilted away from the sun. And that essentially kind of gives you the different seasons that are experienced on the Earth. So you have winter, spring, summer, and autumn. And those seasons are related to the tilt in the Earth, but also then the Earth's location on its orbit or on its journey around the sun. We look at those in a bit more detail. So it takes 24 hours for Earth to rotate or turn all the way around, and we call this a day. As the Earth rotates on its axis, different parts of the Earth face towards the sun and other parts face away from it. So imagine if the sun is over here, so this half of the Earth will face towards the sun, whereas this half here will be facing away from the sun. So daylight occurs on Earth when it faces the sun, and night occurs when sunlight does not reach the Earth. So for example, if the sun is here, then this portion of the Earth will experience daylight because it's facing towards the sun, and this portion of the Earth would experience nighttime. And then as the Earth rotates around, so you can imagine like this section here is going to move right around here, and it's going to move into direct, like it's going to face the sun, and it's going to experience daytime. So as the Earth rotates around like this, you get day and night. So this is what's happening. So you have the sun here like this, you have the Earth. The Earth is rotating on its axis. The axis is slightly tilted, and essentially what that does is it creates like this. It creates a dark side and a light side on the Earth. If your country is in the light side of the Earth, it's experiencing daytime, and then as time moves on and the Earth rotates around, your country will move into the dark side, and then it'll experience nighttime. And this continues on. This pattern continues on every day, 365 days a year, and it'll keep moving on like that. So that's a pattern that we observe here on the Earth, and it relates to the relationship between the Sun and the Earth, and then also in relation to the rotation of the Earth then as well. So sunlight as well, it travels in a straight line. So another thing to kind of think about as well is that as the light travels through space and hits the face of the Earth, this side is going to warm up, whereas this side is going to cool down. Temperatures will start to cool down as well. Parts of the Earth, so for example, the center of the Earth in the equator, the sunlight is going to be hitting it directly on, so it's going to heat up the Earth more. Parts of the Earth, for example, up here and down here, the light is going to hit the Earth at an angle, and it's not going to be as intense as the heat from the sun down here, for example, in the equator countries. So Earth's axis, Earth's tilt. The Earth's axis is tilted at, as we mentioned, 23.5 degrees from the plane of its orbit around the sun. The tilt of the Earth's axis is responsible for differences in length of night and day. So we have different, like for example, the different lengths of day and night, and the seasonal temperature changes that we observe as well. So during the summertime, it's nice and warm. During the winter time here in Ireland, it starts to get cold, and all of that is as a result of the tilt on the Earth's axis and its relationship to the sun as it revolves around the sun. So the tilt of the Earth affects the length of daylight and night experienced over 24 hours. As the Earth orbits the Sun, the tilt of Earth's rotation changes relative to the direction of the Sun. Days are shorter in the northern hemisphere during the winter because the northern pole is tilted away from the Sun. In the summer, the North Pole is tilted towards the Sun, and the days are longer in the northern hemispheres. So, in equator regions, the length of days and nights doesn't change all that much as well. So because there's this tilt on the Earth, so light from the sun travels in a straight line. So if we take the middle of the Earth, the equator of the Earth, so the light hits that pretty much the same all the time. So there's not a huge change as the Earth rotates around the sun. The way that the light is hitting the equator countries isn't really changing. So therefore, you don't really get a change in the day and the night cycle, the length of the day and the length of the night, and the temperatures then. But in relation to the northern and southern hemisphere countries, because there's this slight angle on the Earth, some regions of time in the hemispheres are spent where the Earth is tilted towards the sunlight, and then other times on its journey around the Earth, those same hemispheres will be tilted away from the Earth. So, and that has a huge impact in relation to the seasons and temperature. So at the North Pole, so for example, during the summertime, you can have 24-hour periods of sun or daytime, and then at periods of time, then when it rotates and goes around to the other side on its journey, you can have 24-hour darkness last for almost 11 weeks at its peak in winter as well. So that's the extremes that you're kind of getting in the northern hemispheres in relation to the tilt on the Earth. So as the Earth orbits the Sun, the northern and southern hemispheres are put into and out of direct sunlight. So the part of the Earth tilted towards the Sun gets more direct sunlight than the part tilted away from the Sun and feels warmer. In the summer, the northern hemisphere is in direct sunlight and receives more radiant heat energy from the Sun than it does in the winter when it's tilted away as well. So you can see here, because of this tilt on the Earth, so for example, the equator or the middle of the Earth, okay, sunlight strikes the most, it just hits it dead on and hits directly, okay, so they're going to get, it's going to be hotter and there's not going to be massive changes in in their day and the length of their day and their night cycle. But if we look up here, so as we start to move up towards the northern and the southern hemispheres, what starts to happen is instead of the light directly hitting the Earth, it starts to spread out. And as a result of that, these regions of the Earth are not getting, they're not, there's an angle on the light, so therefore it's not heating up the Earth as much because the heat is not as focused, it's kind of spread out more. So as a result, as you start to move up towards the North Pole or down towards the South Pole, the temperatures start to decrease. But also then as well, and that's related because of the way that the light is hitting the Earth at those points. So because of Earth's axial tilt, it orbits the Sun on a slant, which means different areas of Earth point towards or away from the Sun at different times of the year. So remember, this is the Sun, and then this is the journey of the Earth around the Sun during the year. So remember, 365 days is a year, so that's how long it takes for the Earth to rotate around the Sun, and that's what a typical year is. But as the Earth moves around, because of this tilt, at certain points, sections of the Earth are going to be tilted towards the Sun more, and as it moves around that tilt, it's going to tilt away from the Earth. So for example, if we take the extremes here, so let's say at this point here, so the countries here, for example, are going to be tilted towards the Sun, so they're going to kind of experience summertime here. But as it moves around and it gets over here, like nearly halfway into the year, this same section is going to be tilted away from the Earth. Okay, so it's going to be tilted away, and that tilting away from the Earth results in results in shorter days, and then also results in lower temperatures as well, because the light isn't hitting it directly. And then what happens is, if we look here, so for example, the northern hemisphere is going to experience summertime at this point, the southern hemisphere down here will experience wintertime because it's tilted away from the Earth or the Sun. And then as it moves over here, the northern hemisphere is going to be tilted away and the southern hemisphere is going to be tilted towards, so you're going to get this reverse, if you like, in the seasons. And then the same here, so if we take spring and autumn, the degree at which the Earth is tilted away and towards the Sun is starting to change. So because of the Earth's axis, because of Earth's axial tilt, it orbits the Sun on a slant, which means different areas of Earth point towards or away from the Sun at different times of the year. In summer, the North Pole is tilted towards the Sun, and the northern hemisphere gets more of the Sun's direct rays. This is why June, July, and August are summer months in the northern hemisphere. So this is the northern hemisphere in the summer months. At the same time, the southern hemisphere, which is down here, points away from the Sun, creating winter during the months of June, July, and August. So down here you have it's winter time for these countries down here during those months. Summer in the southern hemisphere is in December, January, and February. So in the southern hemisphere, so if we take our winter time here in Ireland, the southern hemisphere is December, January, February, when the South Pole is tilted towards the Sun and the northern hemisphere is tilted away. So it's this tilt, like this is how important the tilt is. It has a massive impact on the temperatures that are observed on the Earth during those different periods of time. So then we have these ideas of the solstice and the equinox. So the solstice occurs when the angle of the Earth tilts towards or from the Sun at its maximum. So for example, if we take these 2 points here, so during the summertime, so around June 20th to June 22nd, so this is where, for example, you have the Earth, so the southern hemisphere or the northern hemisphere is tilted most towards the Sun, and the southern hemisphere is tilted most away from the Sun. So that happens. So you have at that point, it's roughly June 20th, June So around in the month of June, the 20th and the 22nd. So that's what's known as the summer solstice. So then as the Earth revolves around the Sun, this is the second point, and it's what's known as the winter solstice. So again, this was reversed. So you have the northern hemisphere is tilted. It's tilted maximally away from the Sun, and the southern hemisphere is tilted maximally towards the Sun. So in the summer solstice, so that's at this point here, the Sun is at its highest point in the sky, and this is the longest day of the year. So at this point, this is when you're experiencing the longest days of the year. Why? Because the northern hemisphere is it's tilted towards the Sun, so therefore it's getting more sunlight for that period of time while it's there. The winter solstice is the shortest day of the year when the Sun is lowest in the sky. So again, the winter solstice over here for the northern hemisphere, they're going to have the shortest days. So 21st, 22nd of December. At the equinox, so you have these equinox points here. The equinox, Earth's axis is tilted neither towards nor away from the Sun, resulting in a nearly almost equal amount of daylight and darkness. So at these points here, so if these are the extremes, so longest days here, shortest days here, then these points here, when the Earth, so this is kind of like where what are known as the equinox, so equa or equal. At the equinox, the Earth's axis is tilted neither towards nor away from the Sun, resulting in a nearly equal amount of daylight and darkness. So it evens out. And at the equator, the Sun is directly overhead at noon on the two equinoxes as well. So these two equinoxes, if you're in the equator in the middle of the Earth, that's when, so around September, so you have one in September 22nd to 23rd. The Sun is at the highest point in the sky if you're living in the in the equator countries, and the same then in March as well, 20th, 21st. So you have these two equinoxes as well. So that's how the tilt of the Earth and the Earth's revolution around the Sun relates to, for example, the day and the night and the length of the day and the night cycles. So now if we look at the Earth and the orbit or the revolution of the Moon around the Earth. So the force of gravity between the Earth and the Moon causes what's known as tidal locking. Tidal locking results in the Moon rotating about its axis in about the same time it takes to orbit Earth. This results in the Moon keeping the same face turned towards the Earth. Okay, so take like the length of time it takes for the Moon to do one full rotation on its own axis is about it's 29.5 days. So that's 25.9 Earth days. So the Moon orbits the Earth once every 27.3 days. So it's roughly every 27 days. So roughly every month. It also takes approximately 27 days for the Moon to rotate once on its own axis. As a result, the Moon does not seem to be spinning, and the same side of the Moon is always visible towards the Earth as well. So the side of the Moon not visible from Earth is called the far side of the Moon, and not the dark side, as all parts of the Moon experience day and night. So one day on the Moon lasts about 29.5 Earth days. So a day on the Moon lasts a pretty long time. And what's happening is there's this force of gravity between the Earth and the Moon. Okay, so this force of gravity, and that's what keeps the Moon in orbit around the Earth. So the Moon is being attracted to the Earth, but the Earth is also being attracted to the Moon as well. So there's this force of gravity. And this force of gravity results in this, basically what happens is the Moon revolves around the Earth. And remember, the Earth is rotating on its axis, and also as well the Moon is rotating on the axis, but the Moon rotates much slower than the Earth. So it takes roughly like 27 Earth days for one Moon day, if you like. So a phenomena that's experienced on the Earth is the falling and rising, so rising and falling tides. So tides are the regular rise and fall of oceans. Tides are caused by the gravitational interaction between the Earth and the Moon. The tidal force causes the water in the ocean to bulge out on the side closest to the Moon and the side furthest away from the Moon. These bulges of water are what are known as high tide. This leaves other areas of the Earth with less water, resulting in low tide. Because the Earth rotates through two tidal bulges every day, coastal areas experience two high and two low tides every 24 hours. So high tides occur approximately 12 hours apart, and it takes approximately 6 hours for water at the shore to go from high to low or from low to high. When the Earth, Moon and Sun line up, which happens at times of full moon or new moon, the lunar and solar tides reinforce each other, leading to more extreme tides called spring tides. So essentially what's happening here is you can think about this force of gravity. So the force of gravity, as we mentioned, it keeps the moon rotating around the Earth. But also as well, what that force of gravity does is that force of gravity causes, so if you think about all of the water, so the majority of Earth, if you look here, you can see the majority of it's made up of water. But what that force of gravity does is it causes the water, if you like, to kind of bulge. So why is the water like bulging out like this? It's bulging out because it's being attracted by the force of gravity from the moon. Now, so you can imagine if you have 3 points on the moon, A, B, and C. So you point A, which is facing its closest to the moon. So the water here on the Earth's surface is going to feel like a maximum pull from the moon here at point A. Now also as well, the Earth itself is being pulled towards the moon. And then also then as well, what that does is it causes like two bulges to happen. So the water here is being pulled, if you like, bulged out towards the moon. The Earth itself is being pulled in, so it's being pulled across as well towards the moon, and then that's resulting in this other body of water, or this other bulge of water happening here at this other point as well. So then what happens is, so you can imagine if this is you here at this point. So this is, let's say, Sligo, Strand Hills Beach. So what's going to happen is at this point, let's say in the day, you're going to have high tide. And then as the Earth rotates, what's going to happen is this: you're going to move around here like this, and you're going to experience low tide. And then what's going to happen is as you rotate around to here, you'll be experiencing high tide as well. And then as you get to here, it'll be low tide. And this rotation, this like phenomena of the tides will just continue to happen throughout the 24-hour period. So this is, and why is this happening? It's happening because of the force of gravity from the moon. The other phenomena that we can observe on the Earth as well in relation to the moon is the phases of the moon. So when you look out into the sky in the evening time, you have these different phases of the moon. So we want to kind of look at how that happens or what causes that. So the moon doesn't make its own light. So for example, the light that we see that is light that's reflected from the sun to the Earth. It just reflects the sun's light. The sun always illuminates one half of the moon. The sun lights up different sides of the moon as it orbits around the Earth. It's the fraction of the moon from which we see reflected sunlight that determines the lunar phases. So when you look up at the sky, the piece of the moon that you actually see, that piece of the moon is this piece of the moon that's reflecting light from the sun. So the new moon occurs when the moon, Earth, and sun all lie along approximately the same line. Since the sun is behind the moon from the Earth's perspective, the side of the moon that faces the Earth is dark. So it kind of follows this phase. Okay, so this here is what's known as the new moon. So basically, so imagine this is kind of like what it looks like. So the sun, the light from the sun is being reflected out here. This side of the moon that's facing towards the Earth, for example, the Earth is in here, is in darkness. Why? Because it's not getting any of the light from the sun. At first quarter and last quarter, the moon lies perpendicular to the line between Earth and Sun. We see exactly half of the moon illuminated by the sun, the other half lies in the shadows as well. So if we take like these two quarters here, so you have what are known as like half moons. So half of the moon is reflecting light towards the Earth, the other half is in darkness. Here in new moon, none of the surface of the Earth or the moon is reflecting light towards the Earth, so therefore you don't see it. And then here in full moon, if you like, the whole, so like imagine this is the sun, the light is traveling from the sun, hitting the surface of the moon, and then that surface is pointing down towards the Earth, and what we see on the Earth then is this full moon. And these are the lunar phases. So a waxing moon means that the illuminated part is getting bigger. Okay, so you start off with a new moon. Okay, so at this, because of the way that the position of the moon on its orbit around the Earth, and the position of the sun and the position of the Earth, the side of the moon that's facing the Earth is not reflecting any sunlight, and this is the new moon phase. Okay, then what happens is, as it starts to rotate around, a little portion of the face of the moon that's facing the Earth, it starts to reflect a little piece of light. Light starts to reflect off this piece towards the Earth, and then you get what's known as a waxing crescent. So waxing moon means that the illuminated part is getting bigger. Then you have what's known as the first quarter. So a waning moon means that the illuminated part is getting smaller. So for example, down here, the illuminated part starts to get smaller as we move over here towards this. So waning. A crescent moon refers to the appearance of the moon that is less than half illuminated, and a gibbous moon refers to the appearance of the moon that is more than half illuminated. So this is the kind of phase as you go through the month. This is the phases of the moon. Okay, so it goes from new moon to waxing crescent to first quarter to waxing gibbous to full moon, and then it starts to wane then. So you go from waning gibbous to third quarter to waning crescent to back out here to new moon as well. And this cycle just continues to repeat every month. And this here is kind of like this is what it looks like, just kind of speeded up. So as you go through the month and you look up at the sky, the moon, for example, will continue to go through these phases of the moon. So let's kind of look at what's actually happening here. So how does this happen and what causes it to happen? And it's very straightforward. So imagine you have the sun here. And what's happening is light is traveling from the sun and it's traveling down towards the Earth. Now, in order for us, so imagine we're standing here on the Earth and we're looking up into the sky. In order for us to be able to see the moon, light from the sun has to reflect off the moon onto our eye in order for us to see it. So imagine here, so what happens is light travels in a straight line. So you can imagine the light that's traveling here from the sun. At this point, when the Earth, so this is roughly around the start of the month. So when the moon is in this position in its orbit around the Earth, light from the sun is striking the back of the side that's facing away from the Earth, and then it's just reflecting it back out into space. So as a result, when we're looking up at the sky during night at this particular time when the moon is at this particular orbit, no light is being reflected off the surface of the moon that's facing us. So therefore we don't see it. And then this is what's known as a new moon. Now, as the Earth starts, or as the Moon starts to rotate around the Earth, what starts to happen is, so again, we're here at this point, and let's say later into the month, we have a portion of the face of the Earth the face of the Moon that's facing the Earth is starting to receive light from the sun. Okay, so what's happening is then the light again is traveling in a straight line, and it's just striking this portion here. So it's like a little a crescent of the Moon, and that light then is being bounced back down to Earth, where it's going and hitting your eye, and you're seeing this portion here. Okay, but it's only like a little section of the Moon that you can see. Now, what then starts to happen is as the Moon starts to orbit, more and more of the surface of the Moon that's facing the Earth gets sunlight bounced off it down to the Earth. So therefore, we start to see more and more of it. And that's essentially what happens until it gets to the maximum point. So at this point here, for example, the surface of the Moon that's facing the Earth, that is, all of that surface is reflecting sunlight, and therefore we observe that as a full moon. So imagine the light from the sun is traveling through space, hitting the surface of the Moon. That light then is bouncing off the surface of the Moon down to the Earth, and it's hitting our eye, and we're seeing that then as a full moon. And then as the month goes on, the Moon continues to rotate right around, and it starts to go into darkness. And then this cycle just continues on and on and on. So, and these are what are known as the lunar phases, and you can actually track the lunar phases when you look up at the sky each night, let's say in the period of a month. So the next thing then that can happen in relation to these celestial bodies are what are known as solar eclipses. So when you think about an eclipse, if something's been eclipsed, it's been blocked out. So a solar eclipse occurs when part of the Earth is covered by a shadow cast by the Moon, which fully or partially blocks sunlight. This occurs when the Sun, Moon, and Earth are aligned. So like so. During a solar eclipse, the Moon is located between the Earth and the Sun during a new moon. So during a solar eclipse, the Moon is located between the Earth and the Sun during a new moon. Solar eclipses do not occur during every new moon because the plane of the Moon's orbit around the Earth is different to the plane of the Earth's orbit around the Sun. The dark part of the shadow is the Umbra, and the part that is a little lighter is called the penumbra. Okay, so this is what it looks like here. So this is the anatomy of a solar eclipse. So remember, a solar eclipse, you have the sun, solar, sun. So the light from the sun is being eclipsed. It's being eclipsed by the Moon. Okay, so the Moon is, let's say, if you like, blocking the light from the sun hitting the Earth. So what happens then is you have like, let's say, this shadow that's cast. So the shadow so there's going to be a part, like a shadow, if you like, or a section on the Earth when this phenomena happens, that's going to be in full shadow, and that's what's known as the umbra, okay, or full shadow. So you can see here this like kind of middle part here, and it'll cause this like black. If you're standing, let's say, on the Earth at this particular point, you're going to see like a full solar eclipse. Now, again, because the sun is so big and the light is traveling, then you have these other portions here as well that they're like in partial shadow. It's what's called the penumbra, and then this is this section here. So again, a solar eclipse is basically where the Moon blocks out the light from the sun, and we've these two different parts. So you've the part where there's it's completely blocked out, where's this part here, and then this other part here where the light is still, some of the light is able to get past or get through, and it's what's known as a penumbra. And then the other eclipse that you can have is what's known as a lunar eclipse. So a lunar eclipses occur when Earth's shadow blocks the sun's light. Okay, so a lunar eclipse occurs when Earth's shadow blocks the sun's light, which otherwise reflects off the moon. In a total lunar eclipse, the Earth's shadow completely covers the moon. During a total lunar eclipse, the moon appears reddish due to some red light bending around the Earth's atmosphere and reflecting off the moon. And a lunar eclipse occurs when the moon passes directly behind the Earth and into its shadow. The Earth is between the sun and the moon. A lunar eclipse can occur only on a full moon. So what happens is, again, this is a lunar eclipse. So lunar meaning the moon is being eclipsed. So what happens is the Earth passes directly in front of the moon. And again, you have this shadow. So you have the Umbra part, okay, which is in complete darkness. And then you have the pre-Umbra part, okay, and then you have this moon's orbit. So this is what's happening. And then you can have, so during a total lunar eclipse, basically the moon is in the Umbra part of the shadow of the Earth. So it's just in complete darkness. Sorry, during a total lunar eclipse, the moon appears reddish due to some red light being bended around the Earth's atmosphere and reflected off the moon. So what's actually happening is some of this light, it's not in complete darkness, but some of the light gets through and it's reflected off the moon, and you get this what's known as a red moon, or a blood moon. So a lunar eclipse occurs when the moon passes directly behind the Earth and into its shadow. So we have a solar eclipse and then we have the lunar eclipse. And that is that. So we have looked at, let's just go back to our learning intention here. So students should be able to develop and use a model of the Earth, Sun, Moon system to describe predictable phenomena observed on the Earth, including seasons, lunar phases, and eclipses of the Moon. So that's what we've looked at. We've looked at Earth's rotation and revolution, the day and night cycle, the Earth's axis tilt, day length, how this impacts on day length, direct sunlight energy, the seasons. We've looked at the solstice and the equinox. We've looked at moon's orbit and rotation, how that impacts on the tides. We've looked at the phases of the moon, lunar phases. We've looked at solar eclipse, and we've looked at lunar eclipses as well. Okay, thank you for listening.